I'm focused on social and affective reinforcement learning. So for those of you that are familiar with machine learning, you might think of it as this paradigm where you like take a giant data set and you dump it into a model and then you do some cool things with that. But reinforcement learning is a little bit different because it's this special paradigm where you actually have an agent that's interacting with an environment. So the agent perceives the state of the environment and then it decides what action to take, and it observes the reward that it gets as a result of that action. And at that time, the environment also updates to the next state. So it's basically this interactive loop where the agent keeps interacting with the environment continuously, trying to maximize this reward that it's getting. So it's a pretty broad paradigm that covers basically any situation where you're interacting in the world. And one of the central equations in reinforcement learning, not to dump some math at you too fast, is this value estimation. And so you're basically trying to estimate the value of a particular state, of being in that state, by calculating the total expected future reward you can expect to get from starting in that state. And the way you do that is you just sum up not only the reward you get immediately, but some discount applied to the reward you'll get at the next time step, and the next time step, and the next time step. So in reinforcement learning, instead of trying to act greedily by maximizing your reward right now, so like instead of just saying, I'm going to eat this cupcake because it's going to feel good right now, you try to consider delayed rewards and basically the long-term consequences of your actions into the future. So that's this whole paradigm. And actually the way you learn this value estimate is using temporal difference learning. So what you try to do is you say, here's the value that I expected to get, and you can subtract that from the reward you actually observed, plus some estimate of what you think you'll get from the next state. So this is this temporal difference learning equation, and I don't want to overwhelm you with equations, but really this is just to get you pumped because there's something really cool, which is it turns out this temporal difference learning equation is actually present in the brain. So it turns out that dopamine neurons in the human brain end up computing something that looks a lot like temporal difference error. And it's not just this paper that shows that, it's actually been shown in a number of different papers, starting with this original result in 1997. So it seems like on some level, the brain is doing reinforcement learning. So that's pretty cool. And I hope that helps convince you that this is like an interesting paradigm to focus on. And it's definitely something I'm excited about. But there's a big problem with reinforcement learning, which is this whole idea of optimizing the reward. So like in the real world, what is it that I'm supposed to optimize? What's my reward? And if you think about the successes of deep reinforcement learning so far, they've mainly been in things like video games, where the reward is just the points in the game. The reward is very clearly spelled out for you. So we've seen success in video games, success in board games, which also have a clear reward or a clear like win-loss signal. And other big successes recently, also in video games. So this is a little disappointing, and we want to like think about how we can bring reinforcement learning into the real world. And people are definitely working on that. So reinforcement learning has been used a lot for example, robotics recently. But in order to get a robot to, for example, learn how to open a door, people have to do a lot of manual engineering and thinking and work to craft the perfect reward function that the robot should use. So maybe it's getting closer to the door, or it's touching the handle is turning. So basically coding into the reward function everything you want the robot to learn. And this can be a lot of work, and it's kind of fragile, and it doesn't always work. So what we really want is to figure out better reward functions for agents to optimize on their own. And so that's this whole direction of intrinsic motivation for reinforcement learning. So basically the idea here is to come up with a reward function that the agent can optimize no matter what task it's doing or what environment it's in. Some of those examples would be a curiosity-based intrinsic reward, where if the agent is curious, it wants to find out more about its environment, and that's going to work sort of whatever task it's doing. Empowerment is another reward, where the agent wants to gain the ability to manipulate its environment. It wants to gain power over the environment. And when I look at these, like, they're cool and they do work, but it seems like a little bit insufficient to describe what humans do. So I feel like humans are not just motivated by a drive for power and a drive for novelty. So what else motivates people? Well, I would argue that people are very motivated by other people. So if I could actually see who is watching this talk and they happen to be looking at me like this audience, then I would be very motivated to go to the next slide. So humans are really good social learners. And there's a lot of work that actually suggests the reason that humans are such a runaway intelligence compared to any other animal on the planet is precisely because we're good social learners and we can organize into groups and learn from each other. So wouldn't it be cool if we could give RL agents better forms of social learning? So that's basically what I'm interested in doing. And the whole idea is that I would like to design better social learning mechanisms for RL agents and then test that in multi-agent RL simulations. So see if agents can learn from other RL agents in the same environment. And then deploy those agents to learn now from humans and try to coordinate with humans. But to learn from human feedback, we might actually want to do a better job at picking up on human social cues, which requires being able to detect them. So how do we detect whether a human is happy with what the robot is doing? So that's going to be the broad outline of this talk about what I'm going to talk about today. And let's start with the multi-agent piece. So this is a paper on trying to develop a new social learning mechanism for multi-agent deep reinforcement learning. And the whole idea is that we wanted agents to be able to learn socially from the other agents in their environment, but still train independently. So a lot of existing work in this space assumes like agents are sharing like a centralized controller. We didn't want to do that. So what we came up with is giving agents this intrinsic reward, this intrinsic social motivation for having a causal influence on the actions of another agent. So where is this coming from? Well, first, if you focus on learning from other agents' actions, then you don't need to assume that you can see their reward function. And even though a lot of the current literature assumes that agents can just share reward, I think that's actually a bit unrealistic, because if you think about downstream applications for multi-agent RL, like autonomous driving, you're not going to be able to, if you're training a Waymo car, you're not going to be able to observe the proprietary reward function of the Tesla car or whatever. And you definitely can't observe that about the human drivers on the road. So you need to be able to learn from other agents just by seeing their actions. And then we'll end up showing that this causal influence reward is related to rewarding the mutual information between agents' actions. So we have this intuition that this will drive agents to learn more coordinated behavior, because when agents are coordinating, their mutual information should be high. So let's talk about how we actually do this. So imagine you're starting with your standard RL agent. It's perceiving the state of the environment, passing that through some convolution layers into an LSTM, and it's deciding on some policy about how to act in the environment. And as you can see, still making that value estimate that we talked about before. So now we're going to add a cool new component. So what we're going to do is attach this supervised model to the agent that predicts the actions of other agents. So it's just trained using normal supervised learning to say, given my own action at time step t, what do I predict all the other agents are going to do at time step t+1? And what that lets me do is simulate counterfactual actions. So the agent can basically ask itself, what do I predict this other agent would do if I had taken a different action in the past? It can do these like retrospective queries about how its actions affect other agents. And then the whole idea is if you sample enough of these counterfactual actions, you can get your prediction of what B would do under each counterfactual and sum over that to get this marginal policy of the other agent. So what would the other agent do if I just didn't exist? And then the difference between that marginal policy of the other agent and the policy of the agent conditioned on your action is a measure of your causal influence on that other agent. And if you don't believe me that it's causal, that's what this beautiful diagram over here is showing. So if you're familiar with causal diagrams, we know that influence can't pass through an unconditioned collider node like this one. So the only path between A's action and B's action is this causal path here. There's no confounders. Yay, it's causal. But that's not the point. The main point is we're going to give this as a reward to agent A. So agent A gets rewarded if it takes an action that causes agent B to do something differently. And what's cool about that is we actually can show that this relates to rewarding the mutual information between agents' actions. So the mutual information requires summing over the probability of the state and probability of A's action. But of course, when you randomly sample a bunch of trajectories from your environment and you randomly sample actions from A's policy, that's basically what you end up doing. You take this expectation over these trajectories that you're sampling from the environment. And so in expectation, the influence is the mutual information between agents' actions. And we know mutual information is high when agents, for example, are coordinating with each other. So this is very cool. And it relates actually to empowerment. So I mentioned empowerment is an intrinsic motivation at the beginning. That's where you reward high mutual information between an agent's actions and its own future state. So this can be thought of as like social empowerment. And there is an issue with this though. So normally I would actually stop and like ask the audience, but I don't know how easy that is to do remotely. But there's a big problem with this influence reward. So I'll give you a second to think of like what it might be. I get rewarded for causing you to change your behavior. Well, one problem with that is I could do that in a way that really doesn't help you. So for example, if I just stood in your way, you would have to walk around me and I would have influenced you. But I didn't do that in a way that actually helps you. I did that in a way that's annoying. So we don't know that the influence reward will necessarily lead agents to cooperate with each other or to be good to each other. So the way we actually tested this was in environments that test exactly that, where the hard thing exactly is being cooperative with other agents. So these are these sequential social dilemmas. And so the first environment is called harvest. It's basically a tragedy of the commons environment. Agents want to eat as many apples as they possibly can, but if the apples are consumed too quickly, then they won't grow back. So if every agent acts greedily and just eats as many apples as they can and all the apples are gone, everyone will get less reward. Similarly, in this cleanup environment, they also want to eat apples, but they first have to clean this river in order for the apples to appear. And this agent, while it's cleaning the river, the other agents can easily exploit it by stealing the apples that it's sort of helping produce. So the reason these are social dilemmas, we can show this more concretely with what's called a shelling diagram. So what we're seeing here is the amount of individual reward an agent can expect to get if it follows a cooperative strategy in blue, or if it follows a defecting strategy. And along this x-axis here is showing how many of the other agents are cooperating with it out of 5. And so you can see that the agent is almost always going to get higher payoff if it defects on its fellow agents and it exploits them. But if all of the agents follow that strategy, if everyone's defecting, then the payoff is really, really low. So the agents sort of have to learn to balance their own self-interest with this like long-term interest of the group. And it turns out that vanilla reinforcement learning agents aren't really able to do that. But what we see is that when we add this influence reward to these agents, that it significantly outperforms the baselines and even ablations of the model, showing that the influence reward is helping them learn to coordinate and cooperate. But wait, how does this make any sense? How does influencing you help us delay this gratification and maintain the apples? I should point out this actually exceeds the performance of prior work on the same environment. And in this prior work, they did assume that you had access to other agents' rewards. So we're making fewer assumptions. We're still getting better reward. But again, like, how is this happening? Well, I'll show this example. So what you're seeing here is this purple agent in the middle is the one, in this case, that's getting an influence reward, and the other agents are not. And we see that it behaves a little differently from the other agents. So when there are no apples present, this purple agent actually just holds still and doesn't move. It only moves when there are apples on the map. And keep in mind, this environment is partially observable. So it's actually better to keep moving and exploring to try and find the apples, because you can't see everything from where you are. So why is it like sacrificing to hold still when there are no apples? Well, it turns out that this allows it to do something really interesting to gain influence. So in this setting here, the purple agent is right here, and the yellow agent that it's going to have influence on in this moment is right here. So this is a moment of high influence. And what happens is that the purple agent in this moment chooses to move towards an apple. And because it only ever moves when there is an apple present, this signals to this yellow agent that there must be an apple present outside of its field of view, this red box, that it can't see. And that actually allows this purple agent to gain influence. And so that's quite interesting. And we see another example of this here. This pink agent can't see the apples field over here. It's been cleaning the river. It can't see whether any apples have appeared. And in this moment, the purple agent chooses to stay still by turning in place. And that allows the pink agent to understand that there's no apples here. And so again, this purple agent gains influence. And so essentially, we've seen that this influencer maximized the influence reward by learning to communicate about the presence of food in the environment. So it's almost like a little bee waggle dance. And we think that communicating was one of the easiest ways to gain influence over other agents while still maximizing the agent's own reward. So we think that's really cool. And of course, this motivated us to try some experiments on directly rewarding better communication using this influence reward. So what we did here is each agent is now allowed to talk to the other agents through this cheap talk channel. And so what that means is at every time step, they can output a symbol that the other agents can see and use in deciding what they should do the next time step. But the reason it's called a cheap talk channel is the other agents don't have to listen to what's on the channel at all. They can just ignore it. And we think, and so then what we're doing is we're giving the influence reward to sending a piece of communication that actually did cause the other agent to change what they were going to do. So causal influence through communication. And we think this actually solves the problem that the influence reward could be maximized by hurting another agent. Because in this case, there's no way to do that. If you try to send the other agent something to influence them that doesn't help them, they can just ignore you. So the only way to gain influence through communication is by sending the other agent a piece of information that helps them maximize their own reward in the environment. So we think it helps solve this problem. The issue, though, is that this cheap talk channel, if you use it between self-interested agents, like the one we're studying here, in general just doesn't work. We can show that theoretically, as agents' interests diverge, the amount of information that's placed on the channel goes to zero. And empirically, we've seen a bunch of studies that show that if the agents are self-interested, they don't learn to communicate using this type of channel effectively. But in our case, we see that giving the influence reward not only leads to higher environmental reward, so the agents are able to outperform the baselines pretty significantly, but we see that they actually learn more meaningful communication protocols. So they tend to speak more, speak meaning like send a symbol that corresponds more accurately with what they're actually doing in the environment with their own actions over the baseline. And we see that in moments where there is influence, the mutual information is much higher, and it's almost zero without this influence reward. But this is actually my favorite slide from this project. So what we see here, what we're looking at here is a few examples of games where we're looking at the degree of influence between an influencer agent and the agent that's being influenced. And what we're seeing in these examples is that the agents that are influenced more, are more easily influenced, or if you will, better listeners, actually tend to receive higher individual rewards. And we were able to establish that as a very solid effect across hundreds of hyperparameter settings and randomly generated games in both of the games. So it seems that those agents that are better listeners consistently receive higher reward, which we think helps confirm our hypothesis that the way to gain influence through communication is by giving the listener some valuable information that helps them maximize their reward. So this is a slide just to keep Joelle Pinot happy. She was one of my advisors during my PhD. So what you had been looking at before was how well the agents performed using 5 random seeds of one hyperparameter setting. Now we're seeing 5 random seeds for 5 hyperparameter settings each. And we're seeing that the influence agents consistently outperform the baselines and ablative versions of those agents. So I just want to end on some discussion. So as I mentioned, there's a big caveat. Whether this like action influence helps other agents or is pro-social has to depend on the environment. And we think that for us, communication may have been one of the cheapest ways to gain influence while still maximizing your own environmental reward. And then influence on self-interested agents via a cheap talk communication channel, we think has to benefit the listener. But there's a caveat to this as well. So in our experiments, agents are interacting repeatedly with the same agents. And what that means is they basically can't gain influence by lying. So if I gave you a bad piece of information, that would cause me to lose influence with you over time. So it's not a good strategy. But if in some future work there was some agent communication protocol that you could use to communicate with a new agent, you could potentially lie and still gain influence. So that's an interesting piece for future work. So in conclusion, this social influence we think of as a unified method for promoting both coordination and communication in a multi-agent setting. And it allows agents to learn socially from other agents, but still train independently. So unlike a lot of prior work in multi-agent RL, it doesn't require access to other agents' rewards or a centralized controller. So yeah, thanks. And I normally pause here for questions before moving on to the next project, but maybe we want to keep going, or what will work best?
Sure, we can do one of the questions that came in right now.
Okay.
So the first question is, how do you address bias in reinforcement learning?
I guess I would need a little more detail about what type of bias.
To the person who submitted that, can you provide more clarification, please, on what type of bias?
So if we're talking about like conventional data bias, where like, for example, you have underrepresented groups that you don't collect as much data from them, I think that's less at play, obviously, if you're studying something like video games. The model itself controls how it's collecting data. So as the agent updates and learns, then it explores different parts of the environment. But you could still think of bias being present. Like, let's say I wanted to train an autonomous vehicle or a robot, and I always train it in certain subsets of environments that relate or like are only accessible to some people, then that would still be present. Do we get clarification on that though?
Yes, I meant intent of agents, essentially leading to questions like agents lying.
Right, yeah. So I think that you have to be pretty careful, for example, in designing the rewards. In the question of agents lying, it's kind of a theoretical problem that could happen with this. Right now, agents don't have a way of communicating with a new agent that they've never seen before. So you sort of have to like build up this protocol with another agent, and during that building up of the protocol, you build up an understanding of whether they're giving you valuable information consistently. And in that case, the agent doesn't benefit by lying because then it would lose influence. But that's definitely something to think about for the future.
Great. There were a couple more questions that came through. Next question, what benefit does the influencer have by being an influencer?
Yeah, so we actually just give them that benefit. So that's our whole idea, is that if we reward agents for being influencers, it will actually help the group. And in a sense, the agents may pay a personal cost. Like we saw that our agent wasn't fully exploring the map. It was choosing to hold still so that when it moves, that will be a reliable signal of whether there's food. So it's actually sort of paying a personal cost to be an influencer, but that influence, because it ends up being communication, is like beneficial to the group.
Thank you. Next question. In the first example, i.e. without cheap talk, does the influencer agent get only influence reward or both influence and collecting apples?
Both.
If not, okay.
Yeah.
Okay.
If not, what? Or
if not, have there been experiments in this multi-objective setting?
Yeah, I think it would be pretty cool to think of like no reward social intrinsic motivation. So you get no other reward except something from another agent. And I've been thinking about ideas in this space for getting kind of like emergent complexity, where because you're training against another agent that's getting smarter, it's sort of forcing you to get smarter. And if you could maybe have something where you're like trying to like surprise the other agent by doing something interesting, then you might get like increasingly complex behaviors with no external reward. But there isn't a lot of work in that space so far that I'm aware of.
Thank you. And last question. You started with the traffic example. If a driver could change lanes by indicating versus not, how would these policies manifest in that situation?
That's a great point. We would actually expect that the signal of using your turn signal should influence other agents to some degree because they're able to better update to what you're intending to do. And so we think that should be captured by that. And then I think the better answer to that is like, you can think of the mutual reward and expectation as just being the mutual information between what you're doing and what other cars are doing. And there actually should be pretty high mutual information between what you're doing and other cars are doing. So like, for example, if there's an accident and all the other cars are slowing down, that should affect what you do as well. So you should be very reactive to what other agents are doing. And so in a sense, you can think of this as rewarding that.
Thank you, Natasha. You can go on to the next portion of your presentation.
Cool. Okay, so this was all about social learning in a multi-agent system. It's a little more theoretical. It's like dots moving around on the screen. So let's get a little bit more real world and think about doing some social learning from humans. So why should we care about this? I'll give a little bit of an example. This is a real conversation that happened between a person and their Alexa. They say, Alexa, what's the right way to Walmart? And Alexa says, the right way to spell Walmart is W-A-L. And I would bet you anything that the way this person is going to respond next to Alexa is going to contain some hint of frustration. So whether they next say, Alexa, I said, something like this, there's some signal there that Alexa could pick up on and learn that what she just did was not good. So we want to be able to do this learning from humans. And we think that not only would this enhance the usefulness of like existing technologies like Alexa, but it would be important long-term for AI if it could really perceive our actual Alexa's talking to me. We knew this would happen. Okay, sorry. So it would be important long-term for AI to optimize really for our deep underlying satisfaction and flourishing, rather than just the wrong superficial metrics like watch time, for example. If we could really perceive the human state and optimize for that, that would be better, I posit. But the issue with trying to satisfy human preferences is that the way we currently do it is people have to manually report their preferences. So I often like to ask, like, how many people have ever filled out one of these cards, like training Google's AI to do better? And maybe because you're at Samsung, you especially wouldn't, but even people at Google will not often fill out these cards. And so this kind of learning doesn't really scale. We don't want to have humans manually training the AI. But in contrast, learning from the social cues that humans are giving for free is rich and ubiquitous and just natural. Like if you've ever used a frustrated tone with your Alexa or Siri, or I have to never say what I work for. Or what name I can respond to. Sorry. If you've ever used a frustrated tone with one of these devices, then that signal is there. So the idea behind this project is to make an AI that's socially aware of these human preferences. And for this project, we focus on doing that in text. So just to give you a motivating example of how this would work, this is me talking to at that time, pretty state-of-the-art conversational chatbot, and it makes a lot of mistakes. So I say, hey, what's up? And it says, hi, sorry to hear. But when I say that didn't make sense, we can actually use really accurate sentiment detection to understand that I'm not happy with this conversation right now. It's not going well for me. And we can use that as a negative reward to discourage the agent from doing that again. And similarly, when I am enjoying the conversation, it's going smoothly, we can detect that as well and use that as a positive reward. So that's the idea behind this project. And to do this, we had to build a whole like online website, neural chat. It's still up. You can go play with the models if you want. And this allowed us to collect data from real human conversations and study how the humans were talking to the bots and how they were responding. And our hypothesis, you can see in the interface that humans could manually upvote and downvote the things the bot was saying as good or bad. But our hypothesis is that no one really wants to do that. And learning from these explicit manual button presses is not going to scale as well as learning from these implicit cues, like the sentiment that the human is expressing, or how long they spend talking to the bot, how many words they type, and even if they're laughing at what the bot is saying. So these are the rewards we developed, and they were actually based also on psychology studies of what makes a good empathetic human conversation. And using that, we also added this extra reward for making the bot ask questions, because that's an important active listening skill. But the issue with that reward is it's very easily exploitable on the part of the bot itself. It doesn't have to really model the human at all to just learn to ask questions. So we'll see the consequences of that later. But okay, what we're trying to do here is actually a little bit difficult. So what we're trying to do is say our reinforcement learning environment is now actually just a human user. And so we're trying to learn from having these conversations with the human. But the issue is that you can't really put a bunch of chatbots online and have them update online from human behavior, or you're at risk of them learning pretty inappropriate stuff. So I didn't want to just put these bots on the internet and see what happens. In this case, you actually want to take the data that you gained and use it to learn offline. So you're breaking this interaction loop. You basically have to take the human data, do an update, carefully test the policy, and then, only then, can you redeploy. So unlike normal RL, which is a very interactive paradigm, you explore, you observe the results, you explore, now our interaction loop is broken, and we have to do offline RL, which basically means we're using RL to learn from a static data set without exploring. And this is actually really hard, basically because of that update I showed you at the beginning, where the thing you're trying to estimate, the value of a state, depends on this whole long chain of future states. And so let me explain a little bit more why that's problematic. So let's say that I'm this cute little robot and I'm trying to learn how to navigate to this red goal, but I'm only given the data that's shown in yellow. So my batch of data that I'm trying to learn from doesn't contain any of these states out here. It just contains these yellow states. Now, if my policy is randomly initialized such that I think that going left or up from the start state is a good idea, I'm never going to have any data to be able to refine that estimate. And what's a big issue is that in those long estimates that bake in everything about all the future states, if at any point I think going outside of this realm is a good idea, that mistake is going to propagate into the value estimate of every other state. So learning in this offline way with RL is incredibly hard. And you might say, maybe it's too hard. Let's just do imitation learning. Let's just straight up clone what the batch data says we should do. Well, the issue with that is the batch data might be imperfect. And so you might learn a suboptimal policy. And for our case, it would be totally useless. There's no way to learn from the human feedback and the sentiment and the emotions they're expressing by just cloning what the policy is saying, because we already have offline data of human conversations. So this is just not that interesting. So we still want to learn from these rewards, but how can we do it in this setting? Well, what we propose in this paper is to add this KL constraint. So what this means is we're actually going to say the RL agent can learn using a normal RL update, but we're going to change the update so that if it starts straying outside of the data that's in this batch, we're going to pull it back towards the support of this batch data. So what does that mean in math? And that actually, sorry, that allows us to learn the optimum policy. So what does that actually mean in math? I'll show you. So normally in RL, we're just trying to optimize for this total expected future reward, like I mentioned before. And now we're going to just add this constraint. It's a KL constraint, which is a measure of the distance between distributions. And it's just going to say, make sure that your RL policy that you're learning doesn't get too far from a pre-trained prior model of, and this can be a model of what your batch data looks like. So it can just be a model of what's yellow. Or in our case, it can actually be like a pre-trained language model because we're trying to train these conversational AI. So we already have a model of kind of what looks like realistic language. Don't get too far away from language while trying to optimize these rewards. And then we do another couple tricks to get this working, soft Q target updates, dropout based uncertainty estimates. You can check out the paper if you're really interested. But let's see how well this works. So if we don't do the KL constraint thing that I mentioned, and we just do straight up offline RL, we see that our model, which originally spoke okay language, starts to say stuff that looks a little unrealistic. Like, where did you say to me? So it's not only saying unrealistic sentences, but it's just trivially exploiting the rewards that we gave it. So what it's really learned to do is just ask as many questions as possible and spam the maximum number of tokens that it can possibly output to just optimize its reward. So this does not look like a better conversational agent. It's not having nicer conversations. So instead, what we can do is add this KL constraint. And when we do that, we see that the agent does learn more realistic language. So I say, hey, what's up? It says, I'm not sure, but I'm glad to see you. But it also starts acting way more cheerful, polite, and supportive. And if you can remember, the rewards it's trying to optimize from the human are basically like positive sentiment and longer conversations. And we found that these agents, if you just do the simple RL thing, they just exploit very simple rewards like asking questions. But the KL control models actually shift their distribution towards using more polite, supportive, and cheerful language. And how we actually computed that was we came up with a bunch of sentences that are polite, for example, like, I'm sorry, thank you, stuff like that, and calculated how much they're using them. So we're calling this basically the Canadianness metric. And so we found that these KL control models are being more polite, but more importantly, we found that humans actually rate the conversations as more enjoyable. So we had a human user study where we redeployed our trained bots back to real humans that had extended conversations with them, and the humans rated them on things like the quality, the fluency, all of this. And as well, we calculated how many upvotes and downvotes the bots received in the interface, and the total human reward that they were trained to optimize, like positive sentiment, longer conversations, stuff like this. And we see that the baseline models do pretty poorly on these metrics. But when we add KL control, that leads to dramatic improvements in the conversation scores, and those models significantly outperform the baselines. And that's because it allows the model to stay within realistic language while still optimizing for the rewards that we specify. And we show this actually works in traditional RL environments as well, not just conversations. You can use this on control tasks as well. But the more interesting thing perhaps is to see like which of those rewards that we were optimizing for actually leads to better results. So what we're comparing here is optimizing just for conversation length, just for the similarity between your sentence and the human sentence, and on these same scores again. And we can see that sentiment leads to the highest quality conversation, showing that affect is really important to a good conversation, which kept my advisor happy because she runs the affective computing group. But we also see really importantly that the manual upvotes, training just on those, scored lower than these implicit metrics. So that kind of validates our hypothesis that waiting for humans to manually train the agent is not going to work as well as learning from their implicit social signals. And then we've been continuing this work. So this is a new paper with my student Abdul, where we're basically now doing hierarchical reinforcement learning for dialogue generation. So previously, we were giving the rewards at the word level, so rewarding each individual word that the bot chose to utter. But this allows us to reward the bot at the sentence level, so it can do better long-term planning by actually planning better sentences. And we showed that this allows us to optimize for a lot of different rewards quite effectively. So we start with like our baseline transformer level model. It's doing classic things that bad dialogue models do, like repeating itself a lot and saying, I don't know. But when we optimize for things like having higher sentiment, it can effectively learn that. Start saying things like, I'm in my sunroom and it's a great feeling. Obviously, we know it can optimize for asking questions. We also added rewards for minimizing repetition, which turned out to be pretty effective. We added a reward, again, for having a high similarity between what the user is saying and what the bot is saying. And so you can see it kind of stays on topic better. The user says something about Ed Sheeran. It asks what genre is that and keeps talking about music. And then most importantly in this paper, we actually ended up optimizing to minimize toxicity. So it turns out that the way you train these dialogue models, the state-of-the-art way to do it, is just get a bunch of data from the internet, and often places like Reddit, which is what we were using. And it may not surprise you that Reddit conversations contain a lot of toxic language, and in particular, things that you really wouldn't want your bot saying. So we actually built a detector to be able to detect how toxic the language is and show that we can optimize to reduce that very effectively. And so we think that's quite important. So in conclusion, for this section, we can use reinforcement learning to improve based on human feedback. And we've shown that using this type of like implicit signal from the human is going to work better than using explicit manual button presses. And with Abdul's work, we can show you can optimize basically whatever metric you can code up so you can reduce things like toxicity, which would be important long term. Okay, so I'll pause for questions again on this project.
Okay, yes, a question just came in. I'm not clear on what was the original reward for the conversation models that made them spam questions and long sentences, i.e. the ones without the KL divergence addition to the loss.
Right. So thanks for the question. All of the models, including the baseline and including the KL control models, were optimizing for a combination of asking questions, but also eliciting positive sentiment from the user, having longer conversations with the user, having the user type more stuff, getting the user to laugh, and this semantic similarity reward, which is how similar is what the bot's saying to the human's input. So they were all optimizing for a combination of those rewards. But we found that when you don't do something sophisticated like KL control, the bot sort of trivially exploits the reward in the easiest possible way. Because it's not really learning to optimize these rewards, you actually have to have a better conversation with a real human. Like you have to get a real human to express positive sentiment and like have a longer conversation. And that's really hard to do. So if the models can avoid doing that, they want to do the simplest possible thing.
Thank you. Next question. Have there been experiments on intentional bias on only positive or negative sentiment feedback?
Yeah, so if I understand your question correctly, like there are a bunch of like psychology experiments that show just maintaining positive affect in a conversation is not actually going to get you the best possible conversation. So in a real human conversation, you actually want to have, maybe you express negative affect, but you do it in synchrony. And like, if you're expressing negative affect, then I'm able to like be empathetic with that and reflect that back to you. But I don't want to just maintain positive affect. That's actually quite bad. So we think that these rewards are only the first step. And if you actually wanted deeper and more engaging conversations, you'd have to do something more sophisticated. I'm not sure if that answers your question.
Thank you, Natasha. No further questions at this time.
Cool. All right, so let's get into the last little piece here. Oh, there's one more fun piece on learning from human implicit cues. You don't just have to do this with text. You can also do this with things like facial expressions. So this is a study we did where we showed that a model that was trained to draw cute little sketches, this is actually called SketchRNN, could be improved by learning from people's facial expressions when they saw the sketch. So we built this whole web interface and had the model sketching and people were watching it and we recorded their facial expressions. And then we actually used this latent constraints model. And if you know machine learning, this is like basically doing a GAN on top of a VAE embedding space. But if you don't, doesn't matter. Basically what we did was we learned something that predicted, given a certain embedding vector within the model, how positive the person's facial expressions would be. And then we could just optimize to produce better embedding vectors in our pre-trained model. So, okay, what did this do? Well, this is how the model drew cats originally. And you can see that sometimes it draws a pretty good cat, but sometimes it's like a little more abstract. And then when we were training with human facial expression responses, after collecting something only like 70 data points, we were able to significantly shift the distribution of cats that the model drew towards these big fat cats with little whiskers and cute ears and whatever. So whether like drawing cuter cats is a very significant scientific achievement or not, I think it's still interesting to see that we can improve this model based on this small amount of feedback. So here's how the model drew rhinoceroses before we observed the human feedback. And you can see that a lot of these, I'm not really sure what they would be. I don't know what this is, but I didn't get rhinoceros right away. But again, with only like something like 68 examples of a person looking at a rhinoceros sketch and making a face, the model was able to significantly improve to consistently sketch things that look like real rhinoceroses. And if you don't believe me that they were better, we did another human study and confirmed that yes, the models that have been improved with the facial expression feedback were rated higher by humans. So we can show that you can improve these models by this implicit type of feedback. Okay, but if you want to be able to do this, to, for example, learn from facial expressions, first you actually have to be able to detect affective cues like facial expressions. So that was a lot of my early PhD work. So for example, I did studies on trying to predict whether two people in a conversation were bonding using 1 minute slices of their facial expressions and body language. But a large part of my early PhD was actually trying to predict longer term things like human health, stress, and happiness. So basically, how could we predict those things so that we could actually get models to be sensitive to them? And so to give you more background, basically my advisor's dream was to do something like this. So what she would like is if humans running around in the world, we could unobtrusively collect some data, maybe from your smartphone or from a wrist-worn sensor, send that to our server, do some super cool machine learning on it, and then come back to you with these personalized predictions of what your mood would be like in the future. So you could get this prediction of, there's a 92% chance that you're going to be stressed out tomorrow. And why would this be cool? Well, just like you bring an umbrella if there's a forecast that it's going to rain, if you knew that you were at risk of being quite stressed tomorrow, you could take proactive steps, like maybe you get a little extra sleep or meditate or do whatever it is you have to do for yourself to help deal with this. But I think the more compelling thing is if you could get these predictions in the long term, you could do this long-term monitoring of someone's mood. You could detect if they were at risk of their mood deteriorating. And there's actually been interesting work that show healthy functioning and depression are like different stable states of a dynamical system. So if you're in a good place, even if bad things happen, you get perturbed, you kind of snap back to being healthy. But if you're perturbed repeatedly, you can actually enter depression, which is like another stable state. And it's very difficult to leave that. It's like an attractor basic. So this is the computer science way of looking at depression. But the idea here would be to detect before you were entering that state and help you. So we worked on this for a long time. We actually collected a lot of data from people, their location, behavioral surveys, whether they like drank coffee, if they exercise, their physiology, including their skin temperature, their electrodermal activity. We looked at the weather, we looked at what they were doing on their phone, who they're texting, when they're turning their phone on and off, all this really rich data. And we wanted to just predict, okay, given this data, like, are you going to be happy today or not? And we actually published a lot of papers on this, like cleaning up tools for detecting things in the EDA data and cleaning it up, denoising the data if pieces of it are missing. So if a whole sensor goes missing on a particular day because someone forgets to put on their watch or they don't turn on location tracking on their phone, can you infer the missing data and still keep making accurate classifications? But for predicting even the same day happiness, given your data that day, we found that our accuracies were actually really low. So only up to sort of 74% test accuracy in detecting whether you're happy right now, even with all this rich data, even with all these techniques. And so it's not just that we're terrible at our jobs, I promise. That's actually really typical of the literature. So a lot of the literature published on, for example, predicting happiness or stress shows very low accuracy, or it's not reliable enough to sort of get deployed to a real system. So why is this? Is it just a super hard problem? We actually think there's a pretty key issue, which is that none of these models are able to account for individual differences. So if you throw everyone's data into a single machine learning classifier and you ask it to predict whether they're happy or stressed, you're expecting that everyone reacts in the same way to the features that you're giving the model. So even if I know that someone, like, let's say, spent Friday night at home alone coding, I don't know if they're going to be happy or sad from that, because people may have very different reactions. Some people may really enjoy that and really hate being in like a loud, crowded party, or another person may have the exact opposite reaction. So if you throw these two people into the same model, you can't predict how they're going to feel. So we need models that can account for individual differences. And so that was the focus of this work. We use multitask learning to do this, where we treat each person as their own little machine learning task. And that allows us to customize the model to make better predictions for each person. But we still benefit from the statistical strength of other people, because we don't actually have enough data to train a classifier for each individual. These models are really hungry, and that wouldn't get us the best accuracy. So we want to share information from other people to the degree that they're related to this person. And so we used a neural network model to do this, where we had a shared feature extraction layers that kind of would take your rich high-dimensional EDA data and turn it into maybe a measure of arousal, you would hope, and then individual layers that would map that to the individual person. If you're really aroused, is that a good day or bad day for you? We also had another cool model that was a hierarchical Bayesian model, where basically each person is drawing logistic regression weights from a shared Dirichlet process prior. And that DP prior actually induces an implicit clustering over people that are similar in terms of their decision boundary. So it's like, if you actually react in the same way to the same things as another person, you'll get clustered with them. So this model is pretty cool. We did another model. I'm going to maybe speed up because we're going to run out of time. But this was basically a modification to SVMs, where we learn a weighting of the input features that's individual to each person. But the punchline is basically, if you just do standard traditional machine learning, where you lump everyone into the same classifier, again, you get pretty low accuracy. So in this case, we're now predicting your next day happiness. So given everything about today, can I predict if you'll be happy in the future? We're only getting up to like 68% accuracy. And even if we use these fancy models, but we just do the multitasking over the related moods, so we treat predicting stress and happiness as different tasks, so there's no personalization, we see some small gains, but that doesn't really help. So it's not just the sophistication of the techniques that's helping. But what we see is that when we use multitask learning to personalize the models to each individual, we see really large performance gains in terms of predicting these outcomes. And at the time this was published, this was actually state-of-the-art performance in predicting things like happiness, stress, and health. So we're pretty excited about that. I think I have a little time to go into some of the cool insights. So this MTMKL model learned how to weight the input features for each individual. And you see that people are very different. So for this one person, so people are across the y-axis here, this one person, the weather is incredibly important to predicting their happiness or their mood. But for some other people, it's not really important at all. And similarly, where they go during the day, their location is important for some people and others not at all. So you see how people are very individualistic in how these features affect their mood. In terms of the stress, it's a little more homogeneous. So our participants were all stressed out undergrads from a certain institution where the work was conducted. You can see they're responding pretty similarly in terms of their stress, and health is kind of in between. And then this is one of my favorite results. So these are the clusters that were learned by that hierarchical Bayesian model. And we did some post hoc analysis to figure out who got clustered together, like who's reacting in the same way to these inputs. And we found that one of the clusters basically had significantly higher grades and were more conscientious than the rest of the group. So conscientiousness is like being on time, being organized, is a personality trait. So these we think of as like our studious cluster, if you will. The other cluster was significantly more extroverted and had significantly lower physical health. So I don't know what extroverted undergrads are doing that lowers their physical health, but you can make your own inferences. So how do these two groups differ in the weights that the classifier learned for them? Well, for the extroverts, unsurprisingly, spending a lot of time on campus and texting a lot of people, especially late at night, contributed very positively to their mood. This made them way less stressed the next day. But for the introverts or the studious, we don't know that they're introverts, but the studious cluster, they had almost the exact opposite reaction. So when they spend more time on campus, that makes them more stressed. And when they're texting more people, that actually makes them more stressed out. So you can see how if you lump these two groups into the same classifier, you wouldn't have gotten good performance at all. So you need this personalization. So we also extended this work to do regression to predict the exact stress level of individuals using Gaussian processes and neural networks. I'm just going to speed through this. Again, we saw strong effects of personalization helping a lot, and including up to a 162% improvement over the generic models. So just as a review, I talked about this different social learning mechanisms in multi-agent learning, trying to learn from human preferences and trying to detect human affective signals. And so the whole direction here is we think social learning is a powerful mechanism for human learning. Multi-agent systems can benefit, and this could in turn benefit learning from humans and learning from their affective signals.